Friends, welcome warmly to another fascinating conversation. Let's talk about the great philosopher Bertrand Russell. Not an astronomer, mind you, but someone who once shared a brilliant anecdote related to astronomy. During a conference, he explained how the Earth orbits the Sun, and how our Sun itself moves in an orbit around the center of a massive galaxy filled with countless stars. It was a beautiful explanation about astronomy, delivered in a lecture. But then something wild happened. Out of nowhere, in the back row of the conference hall, an elderly woman stood up and interrupted him. She said, "What nonsense are you talking about? All of this is rubbish. Where's the flat Earth? The Earth isn't a globe. It's flat like a pancake, a disc sitting on the back of a giant turtle." What do you think about that? Imagine the faces of the distinguished scientists at that conference. They must have burst into laughter, right? And that's exactly what happened. With a little chuckle, Bertrand Russell responded to the old lady's wild claim. He asked her, "All right, if the flat Earth is sitting on the back of a giant turtle, what's that turtle standing on?" Guess what her answer was? With a hearty laugh, she replied, "Oh, dear scientist, can't you figure it out? That turtle is standing on another turtle, and that turtle is on yet another turtle. It's turtles all the way down." So, friends, here's a story about an infinite stack of turtles, with the Earth as a flat disk perched on the topmost turtle's back. This model of the universe, compared to today's scientific community experimenting with colonizing Mars, launching artificial moons into orbit, and conducting next-level experiments, seems laughable, doesn't it? But here's the thing, friends. We laughed at that woman's idea of a flat Earth on a turtle's back. But what do we really know about the universe? How did our universe begin? How will it end? If the universe had a beginning, what existed before that beginning? What is time? Does time have a beginning? If so, does it have an end? Can we travel through time? Can we transcend it? Honestly, friends, what do we truly know about these things? To put it simply, we've painstakingly constructed models and tried to fit answers to these cosmic questions. We've patched together explanations as best we can. But perhaps in the future we'll find clear, definitive answers to all these questions. And when that time comes, the models of the universe we use today might seem as ridiculous as that turtle stack theory we laughed at. So, with this video, starting from the flat Earth model and moving through every model modern science has created to understand the universe, let's dive into an engaging discussion about the fate of the cosmos. All right, let's begin. Today's conversation starts with how people in ancient times believed the Earth was a flat disk, like a pancake. Around 384 to 322 BCE, the great philosopher Aristotle published a book called On the Heavens. In it, he argued that the Earth wasn't a flat disk, but a spherical object, and he provided two powerful arguments to prove it. You've probably heard these arguments before. The first is about lunar eclipses. During a lunar eclipse, the Earth's shadow falls on the moon, and that shadow is always circular. Friends, this only happens consistently because the Earth is a sphere. If it were a flat disk, the shadow would sometimes be an elongated ellipse or some irregular shape. The second argument is about how the North Star appears. At the North Pole, the North Star is directly overhead. As you travel south, it gradually appears lower and lower in the sky until, at the equator, it's right on the horizon. These two practical observations allowed Aristotle, that great scientist, to powerfully challenge the idea of a flat Earth. But that's not all. Using the distance between two locations in Greece and Egypt where the North Star's position was observed, Aristotle calculated the Earth's circumference to be about 400,000 stadia. Through these observations and mathematical calculations, the idea that the Earth is a sphere, not a flat disk, became widely accepted. People back then also noticed something else. When a ship approaches land from the horizon, you first see the top of the mast, then the sails, and finally the hull. This happens because the Earth is a sphere. Those ancient folks obsessed with observing the stars figured this out. Some of those stargazing scientists even identified other planets besides Earth. Now, Aristotle needed to come up with a theory to explain the motion of these newly discovered celestial bodies. But here's where he stumbled big time. Aristotle proposed a model where the Sun, Moon, other planets and stars all moved in circular orbits around a stationary Earth at the center. This became known as Aristotle's model of planetary motion. In the 2nd century CE, the astronomer Ptolemy took this idea further and refined it into what's called the Ptolemaic cosmological model. In Ptolemy's version, the Earth remained at the center, but the system became three-dimensional. He imagined the Earth surrounded by 8 spheres. The Moon, Mercury, and Venus orbited closest to Earth, followed by the Sun, then Mars, Jupiter, and Saturn, all moving in circular paths on these spheres. The outermost sphere, farthest from Earth, contained all the other stars in the universe, according to Ptolemy. This model helped explain the complex motions of the planets and stars known at the time. But Ptolemy didn't say what lay beyond that outermost sphere. And here's where things get interesting, friends. The Christian Church adopted Ptolemy's model as the standard view of the universe, aligning it with biblical teachings. They claimed that beyond those 8 spheres lay hell and the divine realm. With that, Ptolemy's cosmological model gained the full backing of the Church. However, that model didn't last forever. In 1543, a Polish priest named Nicholas Copernicus dropped a bombshell. He proposed that the Sun, not the Earth, was the center of the universe, and that the Earth and all other planets orbited the Sun in circular paths. This was a revolutionary idea, but the Church's immense power at the time made it hard for Copernicus's model to gain traction easily. Still, the Church-backed Ptolemaic model took a serious hit in 1609 when Galileo Galilei dealt it a devastating blow. Using a telescope, first invented in 1608 by Dutch lensmaker Hans Lippershey, Galileo observed the night sky. He saw small moons orbiting Jupiter, which led him to realize that not everything had to orbit the Earth, as Aristotle and Ptolemy had claimed. Obsessed with his telescope, Galileo kept studying the sky. Around the same time, Johannes Kepler tweaked Copernicus's theory, suggesting that the Earth and other planets orbited the Sun in elliptical orbits, not circular ones. Galileo's observations with his telescope beautifully supported Kepler's idea of elliptical orbits. But there was a problem. No one had yet developed the mathematical framework to prove these ideas definitively. So these competing camps engaged in a long, scholarly debate. That is, until 1687, when Sir Isaac Newton published what's arguably the greatest single work in physics, Philosophia Naturalis Principia Mathematica, or simply Principia Mathematica. In this book, Newton laid out the laws of motion and the equations needed to calculate how objects move through space and time. Using his theory of universal gravitation, he mathematically proved that the Moon orbits the Earth in an elliptical path, and that the Earth and other planets orbit the Sun in elliptical paths too. This turned his model into a mathematically robust one. Scientists and philosophers, who'd previously looked at the universe through purely philosophical lenses, now began modeling it with mathematics. Back then, did they think the universe was expanding or contracting? Honestly, they believed the universe was static, unchanging, and eternal. But Newton's mechanics showed that the universe isn't static, it's subject to change. Early scientists didn't yet know it was expanding, as modern scientists do. Instead, they came up with a clever idea. When the distance between two objects becomes vast, the gravitational attraction between them turns into repulsion. They modified Newton's universal gravitation theory to balance things out, suggesting that the attraction between nearby stars cancels out the repulsion between distant ones, preventing the universe from collapsing. For a while, this infinite static universe model held sway among mathematically inclined scientists. But cracks started to appear. Questions about the universe's origin sparked debates. The idea that an all-powerful God created everything didn't sit well with the scientific community, who preferred evidence-based reasoning over divine attribution. They leaned toward the idea that the universe has always existed and will continue to exist forever. A comforting thought, but still a temporary patch. A century after Newton's Principia in 1787, philosopher Immanuel Kant published Critique of Pure Reason, diving deep into questions like, did the universe have a definite beginning? Is it finite or infinite? Kant called these questions antinomies of pure reason and offered strong arguments for both sides. For a universe with a beginning, he argued that if it began, there must have been an infinite time before it. Otherwise, why would it start at that specific moment? For an eternal universe, he said if it's always existed, an infinite amount of time must have passed, which raises its own paradoxes. Kant's arguments were brilliant, but lacked mathematical backing, so they didn't stick around long. Still, no one had a clear grasp of the universe's origin or nature. Then, in 1929, Edwin Hubble used an advanced telescope to make a game-changing discovery. Galaxies everywhere were moving away from us. This meant the universe couldn't be static, it had to be expanding. If the universe is expanding, then in the distant past, everything must have been compressed into a single, infinitely dense point. This led to the Big Bang theory, a scientific explanation for the universe's origin, wresting the credit from divine creation. But this raised new questions. What happened before the Big Bang? If something did, could it affect the present or future? Here's the kicker, friends. Anything before the Big Bang can't be explained by cause and effect because there's no observable framework for it. Scientists tie the beginning of time to the Big Bang itself, dismissing anything prior as irrelevant. Yet fitting time neatly into the Big Bang isn't so simple. Even with powerful telescopes to observe the solar system, Newton's physics to describe planetary motion, and quantum theory's mathematical models, we still can't precisely define how the universe or time began. But the models we've built work well enough for practical purposes. In science, two main theories explain the universe's origin: the steady-state theory and the Big Bang theory. The steady-state theory, proposed in 1948 by British astronomers Sir Hermann Bondi, Thomas Gold and Sir Fred Hoyle, says the universe has no beginning or end. New galaxies form at the same rate old ones fade, keeping the universe's density constant. But if that balance tips even slightly, the universe would either collapse or expand, weakening the theory's usefulness. The Big Bang theory, sparked by Hubble's 1929 discovery and bolstered in 1965 by Robert Wilson and Arno Penzias's detection of cosmic microwave background radiation, suggests the universe began 13.7 billion years ago in a massive explosion. Still, what happened at or before the Big Bang remains unanswered, leaving the theory heavily debated. Alternative ideas, like cyclic universes or variable gravity, have emerged, but none fully resolve the chaos. Even with advanced science, can we ever pinpoint the universe's and time's origins? Stephen Hawking believed we'd need a unified theory combining Newton and quantum mechanics, a tall order, but not impossible. Some scientists think chasing these answers is futile, better left to uncovering the universe's hidden mysteries instead. Yet others are determined to find clear solutions no matter what. So friends, that's the story of our universe, from a flat Earth to today's cosmic theories.